Imagine your application is running perfectly. Suddenly, everything stops. No errors, no crashes, just silence. In the database world, this is often a deadlock. It occurs when two or more tasks permanently block each other because each task holds a resource the other needs. To understand why this happens, we first have to look at how databases manage concurrency. Most relational databases use locks to ensure data integrity. When you update a row, the database places a lock on it so no one else can change it at the same time. This is usually fine, but when multiple transactions start competing for the same set of resources in different orders, the system can enter a state where progress is mathematically impossible. Today, we're going to deconstruct the deadlock, see how the engine detects them, and learn the patterns to prevent them forever.
Before we can fix deadlocks, we must understand the lock. There are two primary types, shared and exclusive. A shared lock, or S-lock, allows multiple transactions to read a resource simultaneously. It's like a library book that anyone can read in the room. However, when a transaction wants to modify data, it requires an exclusive lock, or X-lock. This is like checking the book out. No one else can read or touch it until you bring it back. The conflict arises because an exclusive lock cannot be granted if any other lock, shared or exclusive, is already held on that resource. The database puts the second request into a queue, making it wait. In a busy system, thousands of these locks are created and released every second, forming a complex web of dependencies that usually resolves itself as transactions commit. A deadlock is specifically a circular dependency. Imagine transaction A locks row 1 and now needs row 2 to finish. Simultaneously, transaction B locks row 2 and now needs row 1. Transaction A is waiting for B to release row 2. Transaction B is waiting for A to release row 1. This is the circular wait. Neither can move forward, and neither will ever release the locks they already hold because they haven't finished their work. This isn't a bug in the database. It's a logical stalemate caused by the order of operations in your code. Without external intervention, these two transactions would sit there forever, consuming connection slots and eventually bringing your entire application server to its knees as more requests pile up behind them.
Modern database engines like PostgreSQL, MySQL, and SQL Server don't just let these transactions sit forever. They have a background process called a deadlock detector. Every few hundred milliseconds, it scans the waits for graph, looking for cycles. When it finds one, it has to make a difficult choice. It must kill one of the transactions to save the system. The database chooses a victim, usually the transaction that has done the least amount of work or is the easiest to roll back. The victim receives a specific error code, like the famous 4001 serialization failure. This rollback immediately releases all locks held by the victim, allowing the other transactions in the cycle to finally proceed. It's a violent but necessary resolution to keep the system alive.
The most effective way to prevent deadlocks is to enforce a strict ordering of resource access. If every process in your application agrees to always lock row A before row B, a deadlock becomes mathematically impossible. In this scenario, if transaction 1 holds row A and transaction 2 wants it, transaction 2 will wait at the start line rather than getting halfway through and creating a cycle. This is why standardizing your data access patterns is critical. Whether you're sorting IDs before a batch update or following a strictly defined hierarchy in your business logic, consistency is your best defense. If you can't guarantee order, you can use try-locks or shorter timeouts, but consistent ordering remains the gold standard for high-performance database design.
Beyond ordering, keep your transactions as short as possible. The longer a transaction lives, the longer it holds its locks, increasing the window of opportunity for a collision. Avoid performing slow network calls or heavy processing while holding database locks. Move that work outside the transaction block. Also consider your isolation levels. While serializable isolation provides the highest safety, it is also the most prone to deadlocks. If your application can tolerate it, using read committed can reduce locking overhead. Finally, always implement a retry loop in your application code. Deadlocks are often transient. Simply waiting a few milliseconds and trying again is often the most resilient way to handle the occasional inevitable conflict in a high-scale system.
Deadlocks are a natural consequence of building robust multi-user systems. They aren't something to fear, but something to architect against. By understanding the circular weight, respecting lock types, and enforcing consistent access patterns, you can build databases that stay fluid, even under extreme load. Remember, the engine is smart enough to detect the problem, but you are the one who must design the solution. Keep your transactions lean, your ordering strict, and your application ready to retry. If you found this deep dive helpful, subscribe for more architectural breakdowns, and I'll see you in the next one.